Hi, this video is going to take you through what you need to know about forces and braking. So we're going to start in this car from a standing start. So initially there is only one force acting, and that is the force from the engine, the thrust. So according to Newton 1, we've got a resultant force, therefore the car will accelerate. This car is going to accelerate up to a steady speed. And at a steady speed, then you can see that there are two forces which are balanced. So, according to Newton 1 again, there's no acceleration. Those two forces are the thrust from the engine and the drag. The drag force is resisting the motion, and that is mainly made up of the air resistance, although there is some frictional forces between the road and the tyre and actually inside the wheel itself. Then, once we decide we're going to need to brake, there is a sudden change from thrust forward to friction backwards. Now again we've got an overall force backwards, so the car decelerates. Now I just want to show you, before we move on, how that is similar in a smaller car but different. So in a smaller car, the situation is the same from the standing start. There's only thrust forwards, so we've got a resultant force, so the car accelerates. Then at cruising speed, there is a balance between the thrust forward and the air resistance backwards. Then finally, there is a friction backwards as well. That means the overall force is now backwards and the car decelerates. But can you see that all of the forces in this situation are smaller than previously? And that is a consequence of Newton's second law, which is the force is equal to the mass times the acceleration. So as Daffodil, this smaller car has a smaller mass, so are all the forces involved in driving it smaller. If it was losing speed from a greater speed, then this acceleration would be greater, and therefore the force would have to be greater to stop it as well. Or indeed, if it was having to stop more suddenly, acceleration would be greater, and therefore the force would need to be greater as well. So now we're going to talk about how do we calculate an overall stopping distance, which is to say the total time it takes to stop a vehicle. I'm sorry, I made the key error there, the deliberate mistake, which is that the stopping distance and all of these things have nothing to do with time. It's the distance the car travels during stopping. First in, it's made out of two things. It's made of the thinking distance, which is the distance the car travels whilst the driver is deciding, if you like, to brake. It's basically the distance that travels during the driver's reaction time. Then the brakes are applied and the car travels a certain distance whilst it's actually slowing down, and the brakes are doing the mechanical work of stopping the car. At this point, all the kinetic energy the car had is going to be turning into heat, in fact, in the brakes. Now there are some things which affect both thinking distance and braking distance, and you will need to be aware of these factors. So factors that affect thinking distance are things such as tiredness, if the driver is tired, if the driver is on drugs or alcohol, and if there are any distractions in the car or outside the car. But also there are factors which affect the braking distance, and those could be road conditions, they could be weather conditions, they could be vehicle condition. So is the road well maintained, or is the weather wet or icy? And are the brakes or the tyres in good condition on the car itself? Lastly, I want to show you how speed affects stopping distance as well. And this picture is directly quoted from the highway code. Now you can see that the faster you go, the longer distance it takes for the car to stop. And it shows you clearly that that distance is made out of the thinking distance and the braking distance. Now this is the interesting thing about this though, is that you can see that the thinking distance increases linearly, as does the speed. See, this is a nice straight line relationship. It's a proportional relationship. So if I double speed from 20 to 40, then I also double thinking distance from 6 to 12. If I go from 30 to 60, then I double from 9 to 18. But the braking distance is not a straight line. Now you can see that it's actually a curve. Okay? And that is because that during this period of time we're dissipating the kinetic energy to heat in the brakes, and this relationship is a consequence of the kinetic energy equation, which I will show you in a later video. So now if we double speed, we more than double braking distance. If we go from 20 miles per hour to 40 miles per hour, we go from 6 meters to 24 meters. In fact, in this case, if we double speed, we quadruple the braking distance. Very interesting. Okay, thank you for watching, and I hope that helped.